Work is related to force and the displacement over which it acts. Consider a constant force F acting on an object of mass m. The object undergoes a displacement d in the positive x direction. The work done by the force is defined to be the product of component of the force in the direction of the displacement and the magnitude of this displacement. W is equal to F cos theta d is equal to F dot d. If there is no displacement, there is no work done, even if the force is large. Thus, when you push hard against a big box, the force you exert on the box does no work. Yet, your muscles are alternatively contracting and relaxing, and internal energy is being used up, and you do get tired. Thus, the meaning of work in physics is different from its usage in everyday language. Thus, no work is done in scenarios the displacement is zero. For example, a boy pushing a car, there is no displacement of the car. Hence, the work done is zero on the car. The force is zero. For example, a ball moving on a smooth horizontal table is not acted upon by a horizontal force, since there is no friction, but may undergo a large displacement. The force and displacement are mutually perpendicular. This is so since for theta is equal to pi by 2 radian is equal to 90 degrees, cos pi by 2 is equal to 0. For example, a ball moving on a smooth horizontal table, the gravitational force mg acting downwards does no work since it acts at right angles to the displacement. Work can be both positive and negative. If theta is between 0 degrees and 90 degrees, cos theta is positive. If theta is between 90 degrees and 180 degrees, cos theta is negative. In many examples, the frictional force opposes displacement of a body, so in that case, theta is equal to 180 degrees. Then, the work done by friction is negative, that is, cos 180 degrees is equal to -1 in that case. Concept of potential and mechanical energy. Part 1. The word potential suggests possibility or capacity for an action. The term potential energy brings to one's mind stored energy. A stretched spring possesses potential energy. When it is released, it assumes its original shape quickly. Thus, potential energy is the stored energy by virtue of the position or configuration of a body. The body left to itself releases this stored energy in the form of kinetic energy. Let us take the example of a box. Let us raise the box up to a height h. The work done by the external agency against the gravitational force is mgh. This work gets stored as potential energy. When released, the box comes down with an increasing speed. Just before it hits the ground, its speed is given by the kinematic relation. V square is equal to 2gh. This equation can be written by multiplying mass m on both the sides. 1 upon 2 mv square is equal to mgh, which shows that the gravitational potential energy of the object at height h, when the object is released, manifests itself as kinetic energy of the object on reaching the ground. A very important point to understand is that the gravitational force on a box of mass m is mg. G may be treated as a constant near the Earth's surface. By near, we imply that the height h of the box above the surface of the Earth is very small compared to the Earth's radius re. As h is less than re. So that we can ignore the variation of g near the Earth's surface. Concept of potential and mechanical energy. Part 2. The dimensions of potential energy are ml raised to the power 2, t raised to the power minus 2, and the unit is joule or J, the same as kinetic energy or work. The change in potential energy for a conservative force, delta V, is equal to the negative of the work done by the force, that is, delta V is equal to minus Fx delta x, where delta x is the displacement due to the force Fx. Physically, the notion of potential energy is applicable only to the class of forces where work done against the force gets stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. Mathematically, for simplicity, in one dimension, the potential energy Vx is defined if the force Fx can be written as Fx is equal to dV upon dx. Integral of Fx dx is equal to integral dV upon dx. Dx is equal to integral dV. Integral xi to xf Fx dx is equal to integral xi to xf dV is equal to V from xi to xf. W is equal to integral from xi to xf. Fx dx is equal to Vxf minus Vxi. The work done by a conservative force such as gravity depends on the initial and final positions only. Energy. One of the most important physical concepts is the concept of energy. Energy is the capacity to do work. Life is impossible without energy. When we eat, our bodies digest the food to release energy so that we can work. When we work or walk, we do some physical work, so here again we use energy. Energy lights our cities, moves our vehicles, and runs our industries. In science, the term energy has a very precise and definite meaning. Energy of an object is defined as its capacity to do work and is measured by the total quantity of work it can do. For example, a man or a horse, when pulls a load, is said to possess energy. If a moving body sets the other bodies into motion after collision, then it is said to possess energy. The mainspring of a watch, when turned around, drives the hand of a watch and does work. It is also said to possess energy. So we can conclude that anything which is able to do work is said to possess energy. So we can say that ability to do work is called as energy. The object which does the work uses energy, and the object on which the work is done gains energy. The unit of energy is same as that of work, that is joules, which is symbolized using the symbol J. Types of energy. How does an object with energy do work? When an object that possesses energy exerts a force on another object, it transfers its energy to the other object. The second object may move it as it receives energy, and therefore it may also do some work. This implies that any object that possesses energy can do work. There are various forms of energy such as solar energy, heat energy, wind energy, chemical energy, hydro energy, electrical energy, magnetic energy, light energy, nuclear energy, mechanical energy, kinetic energy, potential energy, etc. Kinetic energy. You all must have played the game Carom and must have hit the Carom coin with the striker. When you move the striker, it hits the Carom coin and changes its position. A bullet fired from a gun is able to penetrate through some distance into the target. A body can break something on which it falls. Fast-blowing wind can rotate the blades of a windmill. Water in motion can rotate the blades of a turbine. All the above illustrations show that a moving object is capable of doing work because of its motion, and the energy possessed by a moving object is called as its kinetic energy. The energy possessed by an object by virtue of its motion is called as its kinetic energy. The kinetic energy of a body moving with a certain velocity is equal to the work done on it to acquire that velocity. Kinetic energy. Consider an object of mass m, which is moving with an initial velocity u on a perfectly frictionless surface. Let us consider that an external constant force F acts on an object and produces acceleration a in it. If v is the final velocity of the object after having undergone a displacement s, then from equation of motion we have v square minus u square is equal to 2as, which implies v square minus u square whole divided by 2a is equal to s. Work done by the force in displacing the body through a distance s, that is, w is equal to F into s. Also, from Newton's second law of motion we have F is equal to ma. Thus from equation 1, 2 and 3 we get W is equal to ma into v square minus u square whole divided by 2a. This implies W is equal to m into v square minus u square whole divided by 2, which implies W is equal to half mv square minus mu square whole, which implies W is equal to half mv square minus half mu square. Object is initially at rest, that is, u is equal to 0, we have W is equal to half mv square. The work done, W, on the object to make it acquire a velocity v after starting from rest appears in the form of kinetic energy of the object. Is denoted by EK. Thus, the kinetic energy possessed by an object of mass m moving with a uniform velocity v is EK, which is equal to half mv square. Potential energy. Have you ever stretched a rubber band? What happens happens when you release your hand from one of the ends? The band will tend to regain its original length. From where does it get the energy to regain its position? Similarly, take a toy car. Wind it using its key. Place the car on the ground, and the car starts to move. Where does it get the energy from? Water stored in the reservoirs at heights helps in generating electricity. From where does the water get the energy to move the turbines? In all these above illustrations, applied force does not change the velocity, but instead changes its position. The work done by the force gets stored up in another form of energy called potential energy. The energy possessed by an object by virtue of its position or configuration is called as its potential energy. The work done on the rubber band to stretch it is stored as the potential energy in the band. The work done to move the spring is stored as the potential energy which helps the car to move. Similarly, the water at the height also possesses potential energy due to gravitation, and that's why when it gets converted to kinetic energy, it is able to move the turbine. Potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object. Let the work done on the object against gravity W. Work done W is equal to force into displacement is equal to mg into h is equal to mgh. The object gains energy equal to work done on it. So, EP is equal to mgh, where EP is the potential energy. Part 1. We know that energy is available to us in various forms such as mechanical energy, electrical energy, heat energy, light energy, sound energy, chemical energy, nuclear energy, etc. The various forms of energy are interconvertible. Robert Mayer stated that energy can neither be created nor be destroyed. It can only be converted from one form to another, and as such, the total energy in this universe remains constant. This is called as the law of conservation of energy. Loss of energy of one system is exactly equal to the gain of energy of the other system. This law is true for all the situations and for all kinds of transformations. There are many such examples of energy transformations. Conversion of mechanical energy to electrical energy. In this, the potential energy of water stored in dam is changed to kinetic energy when it falls from the height. The kinetic energy of water rotates the turbines to produce electrical energy. When we stretch a bow, the potential energy gets stored in the bow due to change of shape, and then this energy is then used in the form of kinetic energy in throwing the arrow. When we light an electric bulb, electric energy is converted into light energy. When we use a loudspeaker, electrical energy is converted into sound energy. When we switch on an electric fan, blades of fan start rotating as electric energy is converted into kinetic energy, which is actually a form of mechanical energy. When we charge a battery, electrical energy changes into chemical energy. A solar cell converts light energy into electrical energy. Conservation of energy, Part 2. Law of conservation of mechanical energy of a freely falling body. Neglect the effect of air resistance on the motion of the body. Let us consider a body of mass m placed at a point A. The body is made to fall freely from this point. The body reaches point C after some time. S is the distance of point C from A. G is the acceleration due to gravity. V1 is the velocity of the body at C. The body continues to fall and it reaches point B. V2 is the velocity of the body at B, a point just above the ground. H is the height of the body above the ground. At the point A, the velocity is 0, that is, u is equal to 0. Potential energy, EPA, is equal to mgh. Kinetic energy, EKA, is equal to half mu square is equal to 0. Total mechanical energy, EA, is equal to EPA plus EKA is equal to mgh plus 0 is equal to mgh. This is equation 1. Point C. When the body falls from A to C, it covers a distance s. The velocity at C is equal to V1. Using the equation of motion, we get V1 square minus U square is equal to 2AS. V1 square minus 0 is equal to 2GS. Energy at C. EKC is equal to half mv1 square is equal to half m into 2gs is equal to mgs. Potential energy at point C, EPC, is equal to mg into h minus s. Total mechanical energy at C, EC, is equal to EPC plus EKC is equal to mg into h minus s plus mgs is equal to mgh minus mgs plus mgs is equal to mgh. This is equation 2. At the point B, velocity of body at B is equal to V2. From equation of motion we get V2 square minus U square is equal to 2AS. V2 square minus 0 is equal to 2GH. Kinetic energy at B, EKB, is equal to half mv2 square is equal to half m into 2gh is equal to mgh. Potential energy at B is equal to 0. Total mechanical energy at B, EB, is equal to EKB plus EPB is equal to mgh. This is equation 3. From equation 1, 2 and 3 we get EA is equal to EB is equal to EC. The total mechanical energy of the body at points A, B and C is the same. Thus, the mechanical energy of the body throughout the free fall is conserved. As the body falls down, the potential energy goes on decreasing, whereas the kinetic energy goes on increasing. Scientific conception of work. Part 1. To understand the way we view work and define work from the point of view of science, let us consider some situations. Push a book lying on a surface. The book moves through a distance. You exerted a force on the book and the book got displaced. In this situation, work is done. A boy and girl push a car and the car moves through a distance. The boy and girl have exerted a force on the car and it is displaced. Therefore, work is done. Let us look at another scenario. Lift a book to a height. To do this, you must apply a force. The book rises up. There is a force applied on the book and the book has moved. Hence, work is done. A closer look at the above situations reveals that two conditions need to be satisfied for work to be done. 1. A force should act on an object. And 2. The object must be displaced. If any one of the above conditions does not exist, work is not done. This is the way we view work in science. Of work. Part 2. Work done by a constant force. How is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be placed through a distance S in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force into displacement. W is equal to Fs. Let us label it as equation 1. Thus, work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. In equation 1, if F is equal to 1n and S is equal to 1m, then the work done by the force will be 1 Nm. Here, the unit of work is Newton meter Nm or Joule J. Thus, 1J is the amount of work done on an object when a force of 1N displaces it by 1m along the line of action of the force. If we look at equation 1 carefully, can you tell what is the work done when the force on the object is 0? Or, what would be the work done when the displacement of the object is 0? You will find that in both the cases, the work done is 0. In another scenario, the force and the displacement are in the same direction. For example, a boy pulling a box parallel to the ground. The boy has exerted a force in the direction of displacement of the box. In this situation, the work done will be equal to the product of the force and displacement. In such situations, the work done by the force is taken as positive. Of doing work. Part 1. Children, have you ever wondered, do all of us work at the same rate? Do different machines consume and transfer energy at the same rate? Let us look at this activity to understand this better. Consider two children, A and B, of nearly same weight. Both start running separately. Both reach a run for 50 meters. Let us say A takes 15 seconds, while B takes 20 seconds to accomplish the task. Can you tell what is the work done by each? The work done is the same. However, A has taken less time than B to do the work. But can you tell who has done more work in a given time, say in 1 second? Obviously, it is A who has done more work since he has covered same distance in less time. A stronger person may do certain amount of work in relatively less time. A more powerful vehicle would complete a journey in a shorter time than a less powerful one. We talk of the power of machines like motorbikes and motor cars. The speed with which these vehicles change energy or do work is a basis for their classification. Doing work. Part 2. Power measures the speed of work done. That is, how fast or slow work is done. Power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time T, then power is given by power is equal to work upon time. P is equal to W upon T. The unit of power is watt or W in honor of James Watt. One watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joule per second. One watt is equal to 1 joule per second, or 1 watt is equal to 1 joule per second. We express larger rates of energy transfer in kilowatts or kW. 1 kilowatt is equal to 1000 watts. 1 kW is equal to 1000 W. 1 kW is equal to 1000 J S raised to the power minus 1. It is very important to understand that the power of an agent may vary with time. This means the agent may be doing work at different rates at different intervals of time. Therefore, the concept of average power is useful. We obtain average power by dividing the total energy consumed by the total time taken. Average power is equal to total energy consumed upon total time taken.